Awesome. Fantastic. Now, today we are just going to essentially start the second session that we have. The first one, we had some kind of a rigorous stuff on some content, the theory that the overall purpose that we have for this course. Now we just want to jump into something which is very, very, I should say, useful when it comes to, let's say, AI and also statistics. Now, I'm just going to start. If you have any question, please jump in and interrupt me and to ask something. Okay. Now, first of all, I'm just going to start with the concepts of a vector, okay? And the first 5 minutes of the class is a very shallow review of the things that you have done. Then in the next 10 minutes, we are just going to go more into more advanced stuff. Everyone remembers from your high school education, we talked about the vector. We said that the vector is something that also comes not only with the quantity, but also comes, let's say, with a kind of a direction. For example, we said that you have a Cartesian reference frame, which it comes with the normal axis x and y with the origin. Sometimes we come, okay, we said that there is a point here, which we call that, for example, point, let's say, for example, x a, y a, which is the coordinates of that. Then we said that, okay, we can build the vector to show that. And the vector which I have shown doesn't only come with the magnitude, the length, which everyone knows how much is that, square root of xa squared plus ya squared. This is from the high school. But it also comes importantly with the direction. Then as a result, we just came to define this vector. She said that the vector OA, you don't have the physics with me, huh? You don't have physics with me. Okay. And we said that when we come to define it, we call that OA is a vector. And that's why I showed that the vector sign on top of the O and A. And we show that with the coordinates here, which is going to be XA and XB. Or sorry, YA. Okay. This is the thing that everyone is familiar with that. Then when we talk about the vector, brother, when we talk about the vector, it is something that it comes not only with the direction, but also with the magnitude. Now, I'm just going to expand on that thing because we just start for this course. We start from the vectors, then we go to the matrices, then we eventually go to the tensors. Okay. Now, then everything is just built on top of each other. Now, I'm just going to start by saying just, let's say, a vector which I have, which is in 2 dimensions. For example, you can have a vector which is in 3 dimensions or multi-dimensional spaces. For example, if you have a vector in 3 dimensions, when you have, for example, another axis coming from there, you can have a vector. I'm just going to call that, for example, OB, which becomes, for example, comes with the X. For example, I'm just calling it, let's say XA, YA, for example, ZA, which signifies 3 coordinates for that vector. Now I can just move on, build a vector which comes in multitude of the dimensions. Please come in multitude of the dimensions, which it can be n dimensions, which you can call that, for example, ON as a vector, which it comes, for example, x1, x2, all the way to the xn, which is going to be the dimensions. Now, this is the concepts of the vector. We are not going to spend so much time on it. However, today, I'm just going to remind you of the concepts of the matrices, okay? The concept of the matrices becomes like what? For example, I said that if I create an array of these vectors, if I have an array of, for example, a couple of vectors, I push them together. For example, you have imagined that you have, look at this one. You have vector OA, which is a 2-dimensional vector. Imagine if I get 2 vectors from 2-dimensional, I just paste them together. Look at that. For example, I have OB, for example, with another 2 vectors, which I can call that XB and YB. I'm just going to come here, push them together to make something like that. I say, I remember XA, I have YA. I'm just going to put also XB and YB, and I put a bracket both sides. Now you see that this one becomes a little bit different with respect to the vectors that we had, and that's what we call that the matrix. You have heard that before, huh? Yes? Now, with this matrix that we have, well, the matrix is that we are just going to work together in this course. We are just going to call them by the ranking that they have, by the dimensions that they have. First, we say that, okay, the number of the rows of that matrix, in that case, how many rows do I have? Two. I have one row here, two, which I'm going to call that two, the ranking, times how many columns do I have? Column one, column two, row one, row two, which is two by two matrix. That's right. Huh? Which is a two by two matrix, which is an array of the numbers that you had there. Now, we have something which is called matrix algebra. You have also talked about that before. You have learned about the matrix algebra. For example, you know that you can add two matrices that they have the same ranking. For example, you can add two matrices by the order of two by three. Each corresponding element is going to be added to another element. Now, but before we just go there, we are just going to come to just assign an index for each element of that matrix. For example, I look at this element. In this element that I see, for example, which is XA, I'm going to find an address to that. The address which I have for that matrix, for that element, is that identify which row and which column it is sitting at. I know I count the rows from the top to bottom. I count the columns from left to right. Then the XA, which I have over there, it comes with what? It comes with the rank, with the address or with the indices of an element, which I'm just going to call that, for example, X1 by 1 means that it is located at row 1, column 1. This one becomes what? X1, 2 element at the first row, column the second one. This one becomes element, we call that X. Now this is the row 2, column 1, 2, 1. Or this one, it can be, it's okay, it is called Y, but I'm going to call X in general. Early elements in that matrix, you can call it X. But because I'm just going to find the location that they are just standing. And this one becomes X2, 2, which it means that it's located at row 2, column 2. Then when you have that information, you can find that matrix so easily. Huh? So far, so good, everyone. Huh? I'm just going to come to define the very last thing, which is going to be a kind of a review for you before we just jump in to the main discussion that we have. Now, the other thing which I'm going to discuss, we're going to talk later about, let's say, the inverse of a matrix and the transpose of a matrix. Okay, I'm going to talk about those stuff as we move along and as needed. I'm not going to put everything right now. I'm just going to give them when we just come across those kind of concepts. But the first thing that we need for today is the concept of the determinant of a matrix. Imagine I'm just going to define a matrix. I'm just going to call that matrix A. And I'm just going to build a square matrix. Square matrix means a matrix which has the same number of the rows as the columns. It's going to be a 2 by 2 matrix, which means that I have 4 elements total inside. I'm just going to come with this one. I'm going to call that A. I'm going to call that B. I'm going to call that C. I'm going to call that D. A, B, C, D, and D, they can be any real numbers. Any real numbers. Even they can be complex numbers. Okay? Now, what they are going to do is that I'm going to define a characteristic of that matrix. For a square matrix, that they have the same number of the rows as the columns, they have a characteristic number, which is called that the determinant of that matrix. This one, I'm just going to write that DET, which is called the determinant of a matrix. The determinant of the matrix, which I show that it's short by the DET, which stands for the determinants, I'm going to call that parenthesis A, which means the determinant of matrix A becomes what? Becomes, look at that. In this square matrix, look at this diagonal. We call that the main diagonal. The other one, which I have here, which includes C and D, We call them off diagonal. Huh? In that case, we call that the determinant of this matrix becomes product of the diagonal, which means that A times B, minus the product of the off diagonal, which is B times C. If the matrix is square but higher ranking, let's say 3 by 3 or 4 by 4, we are just going to come with a definite formula for that. We do not need to use that at this stage. We just only work for a demonstration for a matrix which is 2 by 2. Okay, now about this one. Another thing that we need before we just jump into the next thing that I'm just going to talk is this. We have two special matrices. These are the two last things which I'm just going to remind you before I talk about the eigenvectors and the eigenvalues and the significance of them in any computations in high dimensions. Like, for example, cancer genomics. The thing that we're going to learn now is extensively used in the gene expression visualization, gene expression analysis. It's a very huge world of the math with this kind of discipline. Now, the last two things which I'm just going to mention before we just go for the main topics are two matrices that are so popular. The first one, they are like Aishwarya Rai in India. Do you know her? Aishwarya? They are in Matrix, they are like Aishwarya Rai, or there was a Khan, there was an actor who was so famous in India. Yes, there are two popular phases in the matrices. The first one, we call that a zero matrix. The zero matrix, I'm just going to call that O. It comes as a matrix that if it is a 2 by 2 matrix, all the elements are zero. This is 3 by 3 matrix, all elements are zero. It means that every element is zero without any exception. It becomes a zero matrix. Now, the other matrix, which is very popular, like Shah Rukh Khan, is it the one? Yeah. It is, we call that identity matrix. I'm going to call that I. My I sometimes I write it like this. If you see something like that, it means that this is I. Sometimes I forget to write it that way. If you see that, don't get surprised. Oh, what is that? This is also identity. It's I. Stands for identity matrix. I'm going to show that if the matrix is a square ranking 2, which is 2 by 2 matrices, if you have, let's say, a matrix like that, identity, it means that all the elements everywhere is 0 except the main diagonal elements, which they are 1. If I have, for example, an identity matrix, which is 3 by 3, it means that I have a matrix, which is, it has 3 rows and 3 columns. Okay? Is that, for example, I have, look at that, I have here, 1 row, 2 row. Oh, no, no, not a good way. It just seems like the 1. Look at that. Let me just change the color. Identity matrix of ranking 3, it means that every element everywhere is 0 except the main diagonal. Is the main diagonal? It comes with this extension. Huh? It means that here every element is 1, 1, 1. All the elements becomes 0 everywhere. You see? Now, this is a 3 by 3 matrix. All elements everywhere is 0 except the main diagonal, which is 1. Everywhere else you look at that, you see everything is 0, 0, 0, 0. These two matrices is going to be so a kind of a celebrity for today. We are just going to work with them very extensively. Okay? Then this is very important. Now, how much time you have spent so far? Okay, now I'm just going to go with the starting of the next thing that we learn. I'm just going to start. I give the overview of the main thing that we're going to discuss. Then I'm just going to give you a break. When we come back, I'm just going to solve some example for that. Okay, now we're going to use everything that we know about the matrices to construct a key and the golden formula, a golden characteristics that it becomes extremely helpful in any discipline. Now, and this is going to be this. Now, guys, look at this one. Oh my God, I forgot. I had to. No, I'm just going to talk about that. You remember about the matrix multiplication, huh? Let me review that quickly. Then I review this one very quickly. Then we take the break. We come back after the break for the main course. Then they are going to start. Get that. This is, everyone, please look at that. This is very important because the thing that we come back after the break, it is mainly built on this. I say I have two matrices. Imagine I have a matrix. I'm not going to put the elements in there, but I'm going to say that the ranking is n times m. The ranking of the matrix is n times m. What does it mean? It means that the matrix has n number of the rows and n number of the columns. For example, 2 by 3, 2 rows, 3 columns. I make it more general by calling n and m. Now, you have two things you can do. You can multiply a scalar to that. For example, uh, I'm just going to go with an example. I'm just going to come with a matrix, which is so simple. I'm going to call that matrix 1, 2, 3, 4, 5, 6. This is a matrix, for example. I come to multiply to that matrix a number, which it can be by arbitrary, it can be any number. For example, I call it, let's say, 7. I'm going to multiply this matrix to 7. What happens is that you have to take this number, scalar, into all elements in that matrix. It means that, for example, the first element there becomes 7 times how much? That's right. 7, you take 7, multiply to this element, becomes 7. You multiply to this element, 40. You multiply that to this element, 21. The second row, you multiply that to this becomes 28. You multiply that to this becomes 7 times 5, 35. 7 times 6, 42. This is a main rule that if you have a matrix, this is multiplied by scalar, you can simply add that thing into that matrix. As easy as that. Now, as a general rule, which I'm just going to denote it here, I'm going to write this rule here. I'm just going to call that rule number 1. I'm just going to call that matrix n m, a ranking of n times m. N can be 2 times 3, like the one which we had. A is the matrix itself. I say that if I have a scalar, I call that the scalar, call it alpha. I say alpha times that matrix, which I did right now, it's commutable with A, n times m multiplied to alpha. Then you see that 7 times matrix is equal as the matrix times 7. They have a permutability of a scalar into a matrix. Okay, this is rule number 1. However, I'm going to come to a very different thing. What? It's okay, don't worry, take it easy. Now, I come to another thing, which is very important. I said that if I have a matrix now, I'm just going to go back on top. I say if I have a matrix, which is n by m, I'm just going to search for another matrix to multiply that to that. Now look at that. This is not a scalar. It's just another matrix. I'm multiplying two matrices together, which you're going to see after the break. We're going to use that rule. I say not all matrices are compatible to each other to become multiplied, right? Now, in that case, in order to be compatible, for example, you want to get married, not everybody is compatible with you. You have to just go for some, for example, testing. That's the test that you have to do. Some people just go for genetic test. Now, this is the genetic test that you have to do for the matrix multiplication. If you want to multiply two matrices together, the matrix which comes after, which is this one, it comes with the ranking. Am I right? These scores which I have taken, it means that empty boxes I have to fill. The testing that you have to do is this. The number of the rows of the second matrix should exactly match this number. It means that this one has to be m. This is the test. If the test fails, it means that they cannot get married. They are not compatible. Now, how about the number of the columns? The number of the columns can be anything whatsoever. I call it P. Can be 5, 6, 7, any number. As long as these two numbers, which are standing closest to each other, the closest ones, which means the number of the columns of the first matrix, the number of the rows of the second matrix, they are equal, you can multiply them, and the end result should come to this. The end result comes to what? Look at that. These two numbers, M and M, that we just check them for compatibility, they're just going to be gone away. We do not have them anymore. But the ranking of the resulting matrix becomes what? Becomes N times P, the things that they are left. This is crucially important. This is crucially important in terms of the matrix multiplication. Then when we come back after the break, we have to do one thing as a process of finding the eigenvectors and eigenvalues. Then over there, remember, the matrix multiplication comes with that rule. As a final thing that I'm just going to finish it before we just go for the break is this. Let me find a very cool color. Yes, got it. Now, a kind of general rule. If I have, for example, matrix A, ranking is N times M, which is multiplied to the matrix, the ranking is M times P, like the one which I did up there. We said that these matrices can be multiplied together because they're compatible. The number of the columns of the first matrix matches exactly with the number of the rows of the second matrix. Then it means that they're compatible. And the N matrix is going to be the ranking of N times P, like the one which I did up there. Look at this one. The question is that, are they going to be the same as matrix B, which is the ranking M times P, times A, which is N times M? Are they commutable, permutable? What do you think? If you are saying no, I'm going to give you a prize. If you say yes, you have to stay here, you do not go to the break, I'm going to talk to you further. Yes? Everyone agrees, huh? Huh? They are not compatible because look at the left. Look at the left. Look at the compatibility test. I have M and M, they match. That they satisfy the compatibility for the multiplication. Look at the right side. This is P, this is N. They are not the same. Means that they cannot even be multiplied together. Then as a result, I call it rule number one. I call it rule number two. Multiplication of any scalar into a matrix is permutable. We can change this spot. But the multiplication of two matrices, they are not permutable. We cannot change the order of the multiplication. This is a very important thing that we're just going to use that when we come after the break. Any question? Huh? Everyone's okay? Happy, happy? Okay, now, okay, now I'm just going to go to the next one. Hopefully, I can finish it by a very simple example for today, but let's give us our best. Now that we talked about the matrices, I'm going to come to talk about something which we call it a characteristic equation for matrices. And this is this. Imagine everyone that we just start by an arbitrary matrix, which I call it A. Huh? I call it A. I'm going to say that based on the laws that you learned for the matrix multiplication, I can find an, another matrix,
which I'm
which
just
I'm
going to
just
call
going to
that,
call that,
if
if
you
you
please,
please,
double check
double
that
check that
on
if
mute.
I'm mute.
Let me
Let me
see.
see.
Heartbeat.
Heartbeat.
Catch
Kaja.
up. Let me
Let me
mute.
mute. I'm gonna press the button here to mute all. Okay. Now, what I'm gonna do is that This note that detect is the most important one for the submission. I said that imagine I start, I have a matrix A. This matrix can represent the gene expressions from a cancerous tumor. It can come with any dimensions, a high dimensional matrix. I can come to search for another matrix, which I call it X. Why do I call it X? Because it's still I have no idea of the identity of that matrix. I'm just going to call that X because I do not know what is that. But A, I have given that. I know what is A. It can be a gene expression of a cancerous tumor that you have sequenced the gene, whole exon sequencing. You got the expression for each gene parts of the mRNA that they have, then you create a matrix for that. For example, for that gene, you read that much. For that gene, you read that much. Then you create a matrix. Then now you come to find a matrix from nowhere. You close your eyes, you find the matrix. You see that it's not as easy though. You call it X. You see that if you multiply these two matrices, it becomes a very interesting thing. You see that you still get the same matrix, which I called it X, which you find it from nowhere. However, it becomes something like that. And lambda, let me call it alpha because that's here with the thing which we had before. Look at that. On the previous slide, I said here, yes, the alpha you multiplied. Let me be consistent. I'm going to call that alpha. Then you see that there is some scenarios that you have been given a matrix. You can multiply that to a matrix unknown. The result is equal as you were multiplying that matrix into an scalar. Huh? This is a very important equation. This is a very, very important equation. And you really want always to find something like that. For example, if you are working in bioinformatics, you have the matrix of the gene expressions of the sequencing of the cancerous tumors. You're always searching for this equation in there. You're going to see why. You're going to see next week why it is very important clinically, why this is very significant. If this equation happens, you can be also happy. We just call this equation organ function or organ equation. Organ equation. Now, this equation, if you find it, for the case of, let's say, the gene expression of the cancerous tumors, it comes with some uh, terminology itself. The first terminology is this matrix that we were able to find. Look at this one matrix. This matrix that we are aiming to find it. This matrix, it becomes like let's say, uh, the governing matrix for our analysis. We call that what? Organ vector. It contains a lot of information when we find it. Another one, and also the same X. And another one which we have here, look at this one, this real number. It's a real number or a complex number, anything. We call that organ, EIGEN value. We call that organ value. Then you see that from here, we are talking about something very intricate. For example, everyone comes from the biology background, from the healthcare background. You know what is a gene. And everyone knows what is a gene transcription, the mRNA, messenger RNA. Everyone has heard about the gene sequencing. Everyone has heard about that, huh? For example, you count the number of the mRNA for that gene. I want to ask you, please come to the front. Okay, please come to sit at the front. I love to see you more. Come to the front. I can't see you there because all the people there, you get lost in my vision. Come to the front. I want to see you more. Thank you. Now, look at that. Now it becomes eigenfunction. We had eigenvalues and eigenvectors. Everyone is okay so far? Okay, now, as I was saying, I was talking about the gene expressions. Remember, if this is want to make a connection to what you have learned so far, you remember when you talked in biology, you talked about the whole genome sequencing. You remember you had many thousands of the genes in the, for example, Illumina sequencing. You counted the number of the RNAs, which is transcribed by that gene, and you can build a matrix. You can say at this row, for example, this row represents this gene, and this is going to be the number of the counts that you got. And then you see that you can represent the genome sequencing of a cancer by a matrix. That matrix can represent A, which I have there, that can represent that real phenomena. But what is X? Still we do not know. What is alpha? Still we do not know. But we know what is A. Now, I'm just going to take one more step further. The thing which I'm going to do, it comes from a very basic algebra. You are familiar with that. I'm just going to take the second right, the right-hand side of this equation to the left. What I'm going to get, I get the matrix A, which can be the matrix of the gene expression of the tumor, times X, which I have the eigenvectors, as I called it. The right-hand side come to the left, now becomes minus alpha X. Does it make sense so far? Yes? Yes? You see, now you are sitting there, I can hear you even better. You see? Guys, for here. Awesome. Great job. Great job. Now, I did that thing. Then I have ax minus alpha x. What I'm going to have on the right side? 0. Because I took everything to the right one side. The other remaining side represents 0. Now, everyone remembers a common factor from elementary school. What is a common factor in this expression? X, exactly. Thank you. Then what do you do with the common factor in math? Factor it. I'm going to factor it. Yes, exactly. Thank you. I have X over there, which is the matrix, which is still I do not know what is that, the eigenvector. The first term becomes A minus alpha becomes what? 0. Now, there's a problem. And the problem for me, actually, there are two problems. There are two problems. I do not see you fine. You are so far behind everyone. Do you want to come to the front? Oh, you're okay there. You're okay? But I do not see you sometimes fine. No, it's okay. Sit there. But now, the next thing which I'm going to do, I have two problems here. The first problem is this. I really look at inside the parentheses. The first element there, this is A. This is a matrix. A matrix which it comes with number of the rows and the number of the columns. What is alpha? Alpha is a number like 2, 3, any real number, not 0. Huh? Any number. But there's a problem. I say a matrix minus a number means, for example, this college minus this pen. What is that? What is the end result if you subtract it from there? A coffee minus my bag. This is ridiculous. Now, that's that they're not compatible because you cannot subtract a matrix from a number. An elephant minus a mouse. It doesn't make sense at all. You have to, I love that. Elephant minus a mouse. You have to make them at the same size. That was a good example. Elephant, huge. Mouse is a small. You cannot subtract them because in terms of the size, they are not compatible. What do? You inflate the mouse. You inflate the mouse and the mouse becomes bigger, you subtract them. I'm gonna do the same thing here. I'm gonna inflate the alpha. Very good example, brother. I love that. Thank you. Now, Now, there's a patent for that. It was from you, huh? There was a patent for that, huh? No? Okay, everyone please listen. Now, I'm gonna inflate the mouse. The mouse which I have over there is alpha, the elephant is A. In order to inflate that, how can I do that? Do you remember I mentioned identity matrix? It was a matrix that everywhere there's zero except the diagonal, which is one. I'm gonna inflate the mouse, which is alpha, by the A. Now it becomes the same size. How they become the same size? For example, look at that. If A is a square matrix, this is all a square matrix, which means that the ranking is n by n, means it has n number of the rows and n number of the columns. The identity matrix is also the same size, which is n by n. Now, you have a look at this example which we had before. Look at this one. Look at this one. We had 7, like the alpha, multiplied to something. It gave you another matrix. Now, if I is the same size as the A, you inflated the mouse to become as the same size as the elephant. Now you can subtract them. Now you can subtract an elephant from an inflated mouse because they are not the same size. Now, everyone is so far so good. Yes? Awesome. Now, then the next thing which I'm going to do is this one. I say that there are two terms. They're multiplied together and it becomes zero. The first term is this one within the brackets, and the second term is the x itself, right? You remember from elementary school, you had, for example, you had two terms, alpha and beta. Alpha and beta, brother, I cannot see you fine. You want to come to the front? Yeah. Oh my God, no resistance. I love it. I love it. No resistance. Thank you. Now, now look at this one. Alpha times beta becomes what? Becomes zero. And now you had two expressions become zero. I have still one spot left over there, waiting for someone. Alpha times beta becomes zero. What did we learn from elementary school? That we can conclude two things. That either alpha becomes zero or beta can become zero. You remember that from elementary school? You have, you have, you have my pen times my cell phone becomes zero. Either this is zero or this is zero because zero multiplies to anything becomes zero. Then you have two things multiplied together. One of them is enough to become zero, right? If that's the case, I'm going to look into this expression. I'm going to connect it to this. It means that either x has to be zero or a minus alpha I has to become zero. I put or. And now we come here to say that if x becomes zero, it's a problem because x, we are looking for the x. All the thing that we care right now, we are caring about the x because if you find the x, you do not need to represent that high dimensional gene expressions, which is so huge matrix. You do not need to represent that much. You can have a very shorter version of that to represent that thing. Now, then if x becomes zero, it means that that matrix doesn't exist. And I don't love it. Then I say that this cannot be true. I say this cannot be true. Uh, then the only thing which can possibly be true is that the a minus alpha I becomes zero. Now, in terms of practicality, let's see. I'm just going to go over there, the next page, and I see that in order to find the x, then I have to find this one. I say that A, the matrix which I had, minus alpha times I I know A is an n by n matrix. I is an n by n matrix because we inflated the mouse to be the same size as the elephant. Then therefore they have the same size n. Then this one has to become zero if you just want to avoid x to become zero. However, we just play a trick. We say that in case if it becomes zero, it means that element-wise, they have to cancel each other. I'm just going to come to say that I take the determinant of this matrix has to become zero. This is the trick that we play. What was the determinant? We talked about that before the class of the matrix. The product of the main element, main diagonal minus the product of the off diagonal. I'm going to give an example, then we finish for today then. We continue with that next week because it becomes too long then. Now, and what's the purpose of doing that? And now what we want to do is that, look at my eyes. This is my eyes. This is my eye. I only focus on this equation to solve it for today. I just care about this. I have been given the matrix A, the gene expression of the cancerous tumor. I know the genes, I know the expressions by the mRNA counting that I did. That's a given matrix for me. Identity matrix, is a Aishwarya Rai. Everyone knows her. Huh? It's identical. It's a popularity. It's a popular. We know that everything is zero except the main diagonal. Anywhere you see I in the matrix, you know what is that. Now, then what is not given to me? Alpha. Then the alpha is a thing which I have no idea. I'm going to find alpha. I'm going to give, and then from this equation, which I focus, the thing which I get at the end is to find how much is going to be what? Alpha. That's what I'm going to do now, then to finish today. Now, I'm going to give you an example. I'm going to give a matrix to you. The matrix which I give to you is this one. It comes 2 by 2. I have at the first row, which elements 4 and 1. The second row, elements 2 and 3. Right? That's a given matrix. It's the simplest one. Now, I'm going to follow all these things. I know that for this one, I can go to find the eigenvalue function, a times x. How have you been? Good? Huh? Next time I have to bring a chair, just face you there. There is no more seats. I can keep you focused. Now, I have the A. Then there is an equation I can build. AX equals alpha x. I'm looking for the x, but at this stage, I have to start with this one. This equation, we call that characteristic. We call that characteristic equation, right? We call that characteristic equation. Now, for this one, which I have, the first thing which I'm going to do is to form the characteristic equation for that. This is step number 1. And I know that the determinant of this matrix, which is 4, 1, 2, 3, minus, look at the alpha there. Alpha times the matrix 1, 0, 0, 1 should equal to what? 0. This is exactly the same thing. Look at that. No, not this one. This is exactly this expression. The determinant of matrix A minus alpha times I. I is a 2 by 2 matrix. Every element is 1 along the diagonal. All the elements are 0. So far, so good, everyone? Yes? Any question? Any complaints? No concerns? Everyone's happy, happy? Yes? Okay. Look, she's the happiest. Now, what I'm going to do is that to simplify whatever I have in between. Look at this one. Do you remember I said that, brother? Where else do you want to go to see? Now, do you remember I said that if you have a scalar that is multiplied by the matrix, it multiplies to all elements. Alpha multiplies to 1, alpha multiplies to 0, right? Then this one, which I have here, it becomes this. Becomes matrix 4, matrix element 1, 2, 3, minus, if I check alpha, it becomes alpha 0, 0, alpha. Am I right? Right. Now, we have the right point. We have the elephant, we have the inflated mass. Yeah, then both of them come with the same size. This is 2 by 2. This is 2 by 2. Am I right? Now, what's the time for us right now? Is to subtract easily. I say you are the same size, I can subtract you. But how can you subtract them? Look at that. Guys, everyone listen, listen. You have an elephant with an inflated mass, you want to subtract them. Can you subtract elephant ear from the moose nose? No. Ear subtracted from the ear. Eye from the eye. Huh? Then what I'm going to do, it means that correspondence in the subtraction. Look at this. If I subtract them, element 4, it's like the elephant's mouse, elephant's ear. The corresponding for the ear of the mouse is alpha. Look at that. Both of them comes from the same ranking. This is one. This is they are sitting at the same spot, right? Then it becomes 4 minus alpha, 1 minus 0, 1, 2 minus 0, 2, 3 minus alpha. You see, every element subtracted from its corresponding elements, right? So far, so good, everyone. Everyone's happy, happy? Yeah. Now, I get this one. Now, what is this there? Don't forget, I have the determinants of this. And as a reminder, remember, we said that the determinant of a matrix, which is A, B, C, D, is just this number, AD minus BC. It's a reminder. Now, I'm going to take this one, take this matrix. I know that I have to find the determinant of that. I'm going to say now what becomes the determinant of the matrix which I found, which is 4 minus alpha, which is 1, 2, 3 minus alpha, equal to 0. Because what did I have before? I said the determinant. Look at that. I said the characteristic equation, which is this. It requires me to find the determinant of this elephant minus the mouse subtracted together and put it equal to 0. Now, what I'm going to do, I'm just going to find it. You remember, to find the determinant, we got exactly the diagonal, exactly. I have these two, I have to multiply them, which means that 4 minus alpha times 3 minus alpha. Then minus this element times this element. 2 times 1 becomes 2. Write it there. I know that it has to equal to 0. Now we are going back to elementary school math. I have to expand this. In order to expand it, I know 4 is multiplied by 3 becomes how much? 12. 4 is multiplied to alpha minus 4 alpha. I have alpha multiplied by 3 minus alpha. Minus 3 alpha. Minus alpha times minus alpha. Plus alpha squared. And I have minus 2 standing outside. Should equal to 0. Then you see, the next step, I have to make it looks a little bit nicer. How to do that? Look at that. I have 12. I have minus 2. Gives me how much? 10. I have Oh, alpha 2. Do I have anything else? I keep alpha 2 here. I have minus 4 alpha, minus 3 alpha, minus 7 alpha, plus 10, which I had, should equal to what? 0. Fantastic. Guys, what does the equation remind you of? Quadratic equation. Yes? What is a quadratic equation? I'm just going to write it here. Right. I'm just going to write it. Remember, we're going to do this and finish it today. Ax squared plus bx plus c is the general format of quadratic equation. X equals to minus b plus or minus square root of b squared minus 4ac divided by what? 2a. Everyone had this before, huh? Yes? High school or middle school. Everyone had it, huh? Yes. And now look at this one. I'm going to use this formula to solve this. Then what happens? I'm going to say, let me find a very cool color. I didn't use it so far. We'll go with this one. Now, then as a result, alpha becomes, because alpha here represents x. What is b in this equation? That's right, minus 7. Then I have minus 7 plus 7 plus or minus square root of b squared minus 7 times minus 7 becomes how much? 49. Minus, how much is a? 1. How much is c? Exactly, 10 is c. 4 times 10, 40 minus 40 divided by 2a. How much is a? 1. 2 times 1 becomes 2, right? Now, let's make it a little much nicer. Do some kind of housekeeping there. Becomes, I have 7 here, plus or minus. First, inside the square root. 49 minus 40, how much do you get? 9. Square root of 9, 3. Then I have also here 2 as it is. Then you see, uh-oh. Then I get 2 numbers for alpha. For alpha 1, we get 7 plus 3 becomes how much? 10 divided by 2, 5. Another root. 7 minus 3, 4. 4 divided by 2, 2. That's it. Now, what did we do? We find for this matrix 2 eigenvalues. Remember, alpha, we called it eigenvalues. But what we were planning to do from the beginning, we were looking for eigenvectors, because eigenvectors can have information about the matrix A with the highest variation around it that we need to use it instead of the A. But remember, the overall goal that we have is to find that vector, x. But the route to that is find alpha first. Huh? Then as a result, we just find the step number 1. We find the eigenvalues. Our next step is to find the eigenvectors, which contains high level of information about the matrix A. And sometimes we do not use matrix A. We just use X instead because it comes with lots of information about the A, but much smaller and neater. We don't have time to do that. We do this one, eigenvectors, next week. Then I'm just going to stop now here. Next week, we continue from there. We just find the eigenvectors X. Sounds good? Any questions? Any complaints? Any concern? Nothing? Okay, means that we can stop the recording.